Now, to dive a little bit more in the mathematics of matrices, I'm using the material from A.J. Hobson, Just the Math, and I would like to go very quickly through a few definitions. First of all, matrices are an array of numbers which are having rows, the first row, the second row and the third row in this case, and they have columns, the first column, the second one and the third one. An element like this 0 has then, of course, this is then the element A. Since it has the third row, it has an appendix 3, comma 2, because it's from the second column. So the first refers to the rows and the second to the column. Then the order of the matrix in this case is the number of rows times the number of columns. Again, the same sequence. And the square matrix, of course, has the same number of rows as the columns, like in this example in the middle. And if I have only a matrix with one row and one column, what I in fact have is a single number. Or if I have only one column, it is something we already know as a vector, or in this case a column vector, which is vertical, like for instance a column vector like this. Or if it's a row vector, it has only a row and you leave out the commas. Okay, that shouldn't be that difficult. And here you have still an overview, all the elements you see, and for instance here this element again, second row, third column. Then in the case of taking the transpose of a matrix, if I have this matrix A and I'm looking at the transpose one, you see again it is swapped. So what was the row becomes the column and vice versa. Okay, you see this column now becomes the row and so on. If both are the same, like for instance in this example here, we call the matrix symmetric. And if the transpose matrix is the opposite of the original matrix, like for instance in this example, we call the matrix skew symmetric, because if you see if this column becomes a row, you have the same elements, only they change sign. In the case of a skew-symmetric matrix, the diagonal has to have zeros, obviously. If two matrices are equal, it means they have the same elements. Like for instance, this matrix Ax over I, y over z equals 1 over 2 over 3. It means x equals 1, 2, y equals 2 and z equals 3. Well, that's not very shocking, I suppose. What are the operations you can do with a matrix? Well, of course, you can add a number to each element or multiply it with a scalar. I already showed you that. You can take the transpose of a matrix. You can also add matrices. Of course, they need to have the same order. Like, for instance, this matrix here, you can add to this matrix, and obviously you add each element, so the result is then 76. For instance, if I look at the first element here, being the result of 36 and 40, and that goes on for each element. Not very shocking. Well, to make everything complete, I have to mention two other things. Something called the null matrix, which is simply a matrix consisting of only zeros and so on, blah blah blah. And of course, if I have some kind of matrix with numbers and I add the null matrix, nothing changes. So A plus 0 equals A. Not very shocking. Then obviously if I have an inverse matrix, an additive inverse, meaning that I have a matrix and I add the inverse matrix, then obviously the result is then the null matrix. And in this case, this is the additive inverse matrix A. And you see already the word exercises appearing, and that is something we are going to work on now. You can find them at the end of the first paper of Mr. Hobson, and also you find the answers. So, good luck with that.